The goal of a neural net is to arrive at a conclusion with the least amount of error as quickly as possible. One effective way to understand how it does this is by comparing it to a racetrack, like this. Think of a typical racetrack forming a loop. In this example, model training, our runner, will start at the starting line, where it receives all instructions, the rules of the race, from the data scientist. These rules will include crucial details, like the algorithms to use, which activation functions to use in which layers, the number of epochs, and more. The starting point represents the beginning of the forward pass through all the layers of a neural network, where input weight computations are made, and activation functions are either triggered or passed as the model moves through all the hidden layers until it reaches an output. This is where our runner hits the halfway point, as this represents the start of the backward pass. Actual output is compared to the model's predicted output from the forward pass. Loss is calculated and the error is measured, and the model determines how to best adjust the parameters to further reduce the amount of error in the next pass. Model training will repeat in this iterative process through all hidden layers, with each full loop around the track including a complete forward and backward pass of the training dataset. With deep learning models, it is common for datasets to be so large that they must get divided into multiple batches for model training. The number of training examples present in a single batch is called batch size. An epoch is one forward pass and one backward pass of all training examples, so that means all batches in a neural network. Remember that at the very beginning of model training, the data scientist sets forth the rules of the race. This included the total number of set epochs, which can be likened to the length or distance of the entire race. Here, the runner is scheduled to complete 200 loops around the track. Based on selected algorithms, these rules may also include a learning rate hyperparameter, which determines how quickly the machine will learn. In this example, the learning rate can be thought of as the stride length of the runner. Will they be taking large strides or tiny steps? More specifically, learning rate specifies how large or small the iterative weight adjustments will be as it attempts to reduce error and reach global minimum. More on this will be covered later in this lesson. Generally, the rules of the race will impact the bias of each neuron, and thus of the entire model itself. We'll discuss the impacts of machine learning bias with underfit or overfit models next.